This is a Dabble project, which takes a 10-bit binary value from this potentiometer and converts it into a 5-bit BCD value using the Dabble algorithm. Unfortunately, my code doesn't work, so I'll explain it instead. This diagram represents an overview of this project, which is split into 4 main parts. First is a timer 1 overflow trigger source, which will periodically trigger the ADC conversion at a frequency of 1 Hz and uses the timer prescaler's header file, which contains a set of predefined variables. And next is reading the analog input from A5, which is where the potentiometer is, to convert the analog voltage to a digital binary value, which also uses a set of predefined variables, and that is the input to the Dabble algorithm, or also known as the shift and add 3 algorithm, which will convert the 10-bit binary value into a 5-bit BCD value. And finally, that will be printed onto the serial monitor using serial communication. Here's the Dabble algorithm in action, which is crucial for the 10-bit binary value to be converted into a 5-bit BCD number. So in this image, the decimal value is 235, and on each iteration, its bits are shifted 1 to the left, and the MSB of the bits become the LSB of the first nibble for the BCD, and then on each sequence, each nibble of the BCD values are checked if they're 5 or greater, and if they are, 3 is added, and after that they are shifted to the left, and this process basically continues until the original binary value just consists of zeros. So this is the code for the project. First I call the AVR.io library and the prescalers that I described earlier, and then define variables. And then in my main, I call the useSort, which will initialize the baud rate, the character size, parity, and stop bits, and then the IO setup, which will configure the IO ports, and then timer 1 setup, and then call the ADC setup, and then the serial communication. And then after that, I'll call the Dabble algorithm and display it on the serial monitor. And basically you can see each function being defined here with the vector tables as well. So here's the Dabble algorithm, which will receive a 16-bit value, and then maximum value could be 65,535, and that consists of 5 decimal digits, which means there needs to be 5 nibbles, and that's why there are 5 sub-registers in the code from BCD 0, 1, 2, 3, and 4, and each register pair consists of 1 byte or 2 nibbles. And I'm setting an offset of 16 as there are 16 bits. So now all the BCD registers are cleared. I have my Dabble loop, and I'll start with BCD 4, which will move BCD 4 to util, and util is register 16. I want to isolate the lower nibble. Check if that nibble is greater than 5. If not, I'll just skip it. But if it is greater than 5, I'll add 3. This negative sign may look confusing, but it is actually adding 3 to util. Then I want to clear that lower nibble and merge it into BCD 4. So it can be taken together with the other values in the other BCD registers. And this process is basically done with each BCD register pair. And then with each loop, the values in BCD 4 are shifted to the left. And then I do a rotation, which will basically do a carryover onto the next register. And this is done 16 times. And then after I received my decimal value, which is 5 bits, I want to display that onto the serial monitor, and that is done using serial communication with TX, which is transmit, and receive, which is RX.